You've slipped into the event horizon alongside John Michael Godier. Music. For this episode, John chats with Darryl Seligman. Darryl Seligman holds a National Science Foundation postdoctoral fellowship in astronomy and astrophysics, and he's the Simonis NSF Scholar at Michigan State University. His work covers a broad range of planetary science and astrophysics areas, such as minor bodies within our solar system, orbital mechanics of planets, and the beginnings of objects from other star systems. At present, he acts as the early career secretary for NASA's Small Bodies Assessment Group, which influences NASA's plans for studying and exploring asteroids, comets, and similar small worlds. He's involved with the Rubin Observatory Users Committee too. Come August 2025, he'll embark on his new role as an assistant professor at Michigan State. Darryl Seligman, great to have you return to the show. Thanks for the invite, John. Darryl, those chemical puzzles surrounding 3I/Atlas. It's a strange case, and it's gone greenish since our previous talk, with the makeup still puzzling even if the color shift feels somewhat routine, though this instance appears to happen unusually. Got any insights on it? Sure, the shift to green, as you mentioned, is something that pops up occasionally in comets. So, that part didn't shock folks as much as they claimed. But on the composition front, well, there have been a few aspects that caught people off guard, if you're hinting at that. The standout ones were those JWST findings, no doubt. That CO2 pickup was substantial. But I always remind myself this originated from a different stellar neighborhood, under formation conditions we're clueless about. Perhaps there was extra CO2 floating around in that system, or similar. What really baffles me, though, is the nickel-to-iron balance issue. Where's all the iron hiding? I suspect we'll spot it eventually, maybe concealed somehow. What's your take? Yeah, the nickel-to-iron imbalance is indeed puzzling. Let's rewind a bit. You might recall that in 2020 or 2021, it took some time, probably 2021 when it came out, but a Nature paper revealed something comparable in 2I/Borisov. So, it's not entirely new to encounter that. Let me double-check quickly. Yeah, 2021 it was. I can shoot you the paper link, but it involved atomic nickel in the coma of the interstellar comet 2I/Borisov. That left experts scratching their heads back then. And honestly, it might not have gotten the spotlight it deserved even a few years on, mainly because no one knew quite how to interpret it. Now, with 3I/Atlas showing atomic nickel too, or at least that odd nickel-to-iron ratio recurring, it looks like a pattern in these visitors from afar. Exactly. And I'll venture a guess here about the supernova that seeded its home system. Could there be unknowns in how supernovae churn out nickel versus iron? Or might iron get stripped away in the interstellar medium? After all, this object's been drifting through the ISM for billions of years, it seems. How does that affect something like it? Tons of intriguing questions. What's the most recent update on 3I/Atlas as of now? Anything fresh on the Mars flyby data? Spot on. The Mars observations. Yeah, thrilled we're diving into those. And I do plan to loop back to the odd composition, as there are plenty of fascinating angles. One point that might have slipped under the radar deserves a closer look. Potential natural explanations for the iron-nickel dynamic and the CO2 levels. As for the Mars stuff, it's genuinely thrilling right now. The downside is that government shutdown hit just weeks before 3I/Atlas's nearest pass by Mars. It's downright infuriating. No kidding. Ross was messaging me about it too. Yeah, totally infuriating. Just to note up front, I'm not involved in any of those Mars missions. So, I need to tread carefully and not represent the teams or decision makers, since that's way beyond my level. But we had this fantastic chance to examine 3I/Atlas in detail. From Earth, we can't observe it currently. And it's proving to be it's incredibly frustrating, just as you mentioned, because the prime time for a comet's excitement is at perihelion, when it's nearest the sun. That's when the real spectacle unfolds, offering the greatest opportunity to witness the peak activity. Plus, that's your ideal window for gaining the fullest, most accurate insight into the comet's nucleus. Observing it from afar, many volatile materials might be present but remain dormant due to the cold temperatures. Detecting hypervolatiles like CO at vast distances is fascinating, no doubt, but it doesn't provide a complete, impartial picture of the nucleus's makeup. Water, for instance, stays inactive beyond about $4 Australian, since it's not warm enough to sublimate. Right now is the perfect moment to gather key data on C/2019 Y4 Atlas. We knew long ago, upon its discovery, that ground-based views from Earth would be impossible during this crucial phase. We could predict its path well in advance. As aggravating as that timing is for this apparition, we've had months to come to terms with it. Sure, it bummed us out, but we accepted that Earth observations were off the table for this vital period. Many of us, though, pinned our hopes on the Mars orbiters stepping in. The encouraging update, and I think this will please you, is that, to my knowledge, and without claiming to represent the missions, all the space probes scheduled to monitor Atlas during this window, essentially everyone capable of it, are proceeding as planned. Those observations are still underway. The catch, thanks to the government shutdown, is that they can't share any results or data publicly yet. For example, even if the Mars data were fully processed and primed for release, folks can't distribute it. Working at NASA has its ups and downs, as I'm sure you know. I'm not a federal employee myself these days, being a professor at Michigan State, but plenty of researchers, especially those tied to missions at places like Goddard, JPL, or NASA proper, face hurdles. You hear my cats going nuts in the background? Add some flavor to the chat. Yep, we just adopted a kitten, and she's constantly pestering her big brothers. Apologies if that came through. Anyway, back on track. One downside of NASA gigs is the bureaucracy. Even as a co-author on a paper, you need clearance from various offices, depending on your division. So, amid the shutdown, scientists can't even submit work to journals, no matter how ready it is. I won't speak for those on the teams, but I feel for them. Must be insanely aggravating. On a brighter note, it's exciting to think about the imaging from the trusty Mars Reconnaissance Orbiter, one of my all-time favorite probes. It's aged, but remarkably potent still. Absolutely. From what I gather, it'll help pin down the object's true dimensions and settle that debate once and for all. Do you agree? Or were the Hubble shots already conclusive on the nucleus size? Well, yeah. The Hubble Space Telescope observations were super revealing. It was a bit unexpected not to get a tighter size estimate from HSD, but keep in mind how Dave Jewett designs those comet sessions. They're precisely tuned to capture the nucleus dimensions. Measuring a comet's core is tough when it's shrouded in coma. Way simpler for asteroids. Dave excels at configuring HSD runs to isolate and measure that nucleus size effectively. It's challenging to pull that off, but the approach involves capturing an image sensitive enough to isolate the coma and peel it away, revealing just a hint of central glow from the nucleus. That lets you set bounds, like an upper cap on its dimensions, or even spot the thing outright. Take Boru, for instance. Dave managed it with HSD, getting a solid estimate of the nucleus size, complete with the usual margins for error, but impressively precise. Then, for 2I/Borisov, things glitched with HSD. I believe it was a gyroscope problem, though the details escape me. Anyway, they wound up with far fewer observations than planned. I'll need to verify the figures, but it was roughly only 10 minutes of HSD time. Honestly, we ought to appreciate how well it turned out given the mess they faced. Those HSD shots didn't pick up the nucleus, which just establishes a ceiling on its potential scale. Dave's calculation pegged that limit at about 2.3 kilometers, though don't hold me to the exact digit since I can double-check if needed. But it could easily be much tinier, seeing as they never spotted it. More details on the nucleus would be hugely valuable right now, since its scale reveals tons about the object's origins, how it might have formed, and its later history. For example, if it originated in a spot like today's asteroid belt, you'd anticipate that larger bodies rack up plenty of hits, leading to breakups where collisions shatter them, and you'd end up with way more debris in smaller chunks. So pinning down the nucleus size is crucial. I don't want to overdo it, but yeah, John, I'm with you on how thrilling these Mars missions could be for nailing the nucleus measurements. Still, I'd rather not guess too wildly about their success. We'll just have to sit tight for the outcomes, which is annoying. Optimistically, fingers crossed we get it. Realistically, though, keep in mind that none of these space ops, whether they're aiming to watch, prepping to, or already tracking via Atlas, were built around observing an interstellar comet. Some of those Mars setups have cameras pushing 20+ years old. It's incredible they're holding up so well and still operational. But they sure weren't crafted for this task. We should give credit, maybe respect fits, to the crews sifting through this data, because it's way tougher than it seems. They're chasing views of a comet that's relatively stationary near Mars in broad solar system terms. But for the gear on rovers and such, it's insanely distant compared to what those tools were meant to scrutinize or measure. So let's cherish whatever intel comes our way, knowing these mission folks are busting their tails to process, crunch, and make sense of interstellar comet data from instruments never intended for the job. Totally. Yet it's wild how they improvise something workable, and whatever we pull from it will be gold. MRO wasn't built to snap pics of another Mars vehicle descending on a parachute either. I hold those teams in high regard, and I wager they'll extract insights we never saw coming. Any updates from ESA on their probes? Pretty much zilch is out there yet. Like you said, it's echoing that government shutdown vibe without quite being one, but when NASA or U.S. resources hit snags, it ripples to others big time, since the U.S. often chips in, like with many ISS proposals involving. Those global scientific initiatives, what do they call them again? Basically, they're multinational efforts where a big chunk of the team might be from the US or elsewhere. So NASA ends up playing a major role in missions led by other nations, even if they're not the main driver. That's why a US government shutdown spills over big time into the entire worldwide space infrastructure, if you catch my drift. It's seriously damaging, no doubt. But for now, we can stay pumped about the findings rolling in over the next few weeks, like you mentioned. Nothing groundbreaking to spill right this second, though. Sure, but I'm okay knowing the telescopes are still capturing images, right? They're gathering data nonstop. It's just the analysis, sharing it publicly, and all that processing that's on pause. The probes did their job observing, so we'll definitely pull some insights from it, regardless. And hey, even though none of these probes were built specifically for this task, we've got a bunch of them on it. I think there are 4 in total, each with unique sensors. That should make for some fascinating comparisons. Anyway, shifting to the comet's makeup, let me toss out my typical quirky query. Picture a comet from our solar system zooming in and hitting perihelion way nearer the sun. Maybe it starts breaking apart or vaporizing. Does that actually reveal deeper secrets about the comet itself, just from it falling apart that close to the star? Speaking broadly about these icy wanderers. Hold on, let me confirm I'm hitting the mark here. You're asking if, for any old comet, just a typical dirty ice ball swinging by, it's observationally smarter to study it as near the sun as it gets, to really nail down its chemical makeup? Got it, that's a sharp angle. Solid question overall. I'd say the broad answer is affirmative, though with a few qualifiers. For the majority of situations, yeah, and here's why. It gives you the fullest picture of the comet's core. Let's rewind a bit. As a comet approaches the sun, doesn't it? The surface absorbs more solar energy, so increased sunlight photons strike it, warming things up and causing more frozen bits to shift straight from solid to vapor through sublimation. The nearer to the sun, the hotter it gets, triggering various frozen compounds to activate. Take this. Way out beyond, say for AU, 4 times the Earth-Sun gap, you barely detect water activity. It's too chilly for water ice to sublimate aggressively. But draw closer, heat rises, and once a specific ice hits its activation point, it stays that way onward. So if the core still holds that material, it'll keep releasing. You don't want it scorching, but if it's too frigid for a type to mobilize, it simply goes dormant. At heart, the key intel on a comet comes from identifying all the ice varieties present, especially their relative amounts. Like the water versus CO2 balance. Spotting CO2 alone via JWST is a huge win, a real breakthrough. But the game changer is that CO2 to water proportion. The nearer the approach to the sun, the sharper your read on any comet's makeup, since those proportions unlock core truths about it. In a way, those balances matter more to the comet's heart than spotting one element in isolation. And because they reflect the basics, they hint at origins too, like where it might have originated. Say, for instance, you find, purely hypothetical, that when everything's active in the heat, the water dwarfs the CO2. That means any CO2 present would have been sublimating just like the water, signaling the core's richer in water overall. Which points to formation in warmer solar system zones, potentially, since nearer spots favor water buildup over. Yeah, our freeze is solid, but CO2 stays in its gaseous state, No freezing there. Does that track? Totally, it does. You know, it just hit me how fascinating a moment this is for comets, since we're not only dealing with that interstellar visitor like 2I/Borisov zooming by. We've got a pair of solar system ones too. Exactly. They're visible enough for binoculars right now. All three showing up together. Wild, isn't it? Have you managed to catch sight of any yet? Not so far. I figure it'll take a bit longer to pick them out at twilight. Maybe one or two if I'm lucky, whatever I can spot in the evening. But I'll give it a go using my 10 by 50 binoculars, and once I nail down a location, I'll haul out the telescope. I'm planning to hunt them with those large binoculars first because, well, the problem is, Darryl, it's kind of spoiled for me after seeing Hale-Bopp with my own eyes and snapping photos, the whole deal. And nothing's come close to that level. So now, even an old naked-eye comet doesn't really excite me much. Nah, not these days. Hale-Bopp back in the 90s totally wrecked my expectations. Okay, here's my follow-up question. The solar spike on 2I/Borisov that stood out, making me wonder if it was due to some uneven heating effect. What's your take on the process behind that so-called anti-tail? Though it's not a true anti-tail, which is more of an optical illusion with comets from our viewpoint. This one's genuinely happening on the comet itself. What's causing it, in your opinion? Could it be selective beaming from the sun's direction tied to the comet's makeup? There are a few potential explanations, sure. And just to clarify, you're referring to that sunward-pointing tail feature, like we noticed hints of it months back, but the shape of the tail appearing aimed toward the sun. Yep, somehow it seems to be doing that. That's the bit I'm getting at. Right. By the way, that might have shifted recently. Not sure. We can't say for certain, but it could have faded. Still, it was a curious trait. Pretty rare. Yeah, we covered that in reports. I even contributed to some papers on it, but pretty much every image from its discovery up to a few weeks ago, when ground observations got tough, showed the tail structure consistently bent that way. So, it's not without precedent. You spot similar patterns in local solar system comets. It's not the norm, though. Generally, tail shapes reveal insights into the physics at play and the traits fueling the vaporization. One standard example you might have come across. I'm not sure how much comet lore folks usually pick up, probably not a ton, but since I'm dipping into intro astronomy teaching at Michigan State for the first time, I'm realizing how basic the crash course is for most. Oh yeah, people only get the bare essentials. Except, really, hardly anyone even takes that class. Anyway, a go-to fact is that a comet's tail usually streams outward, away from the sun, correct? That's because, as ice on the surface warms and turns to gas, it creates an expanding jet, but there's also fine dust involved. Dust here covers everything from millimeter pebbles to centimeter rocks down to tiny micron specks. So a whole range of gritty, stony bits gets ejected too. Then, sunlight's radiation pressure kicks in. The photons smack those dust bits in the tail and shove them sunward. Often, what you see in those stunning tails arcing away started by blasting toward the sun initially, then got deflected. The most logical spot for initial outgassing, if you picture the comet's surface, is right at the sun-facing side, since that's the hottest part. Man, I wish I could sketch this out, but think of the comet's core like. If you position the sun to shine its rays on one side of the comet, you'll notice that roughly half the surface gets lit up at any moment. That's the section experiencing the strongest warming from the sunlight right then. So, the area that's exposed to the light is where you'd expect the ice to start vaporizing at the most basic level, subliming directly off the surface and drifting toward the sun's direction. Once that's underway, the pressure from solar radiation kicks in, with photons from the sun striking the dust bits in the comet's tail and shoving them outward, away from the sun, while pulling some gas along for the ride. Often, those classic comet tails you see stretching away from the sun are simply the result of this radiation push happening afterward. For instance, after material has been ejected from the comet like in the case of 3I/Atlas, it's still not entirely clear what's driving it. We could use more data. Honestly, we haven't had the chance yet to run thorough numerical models or simulations to pinpoint what might shape the tail structure we're observing, since it hinges on factors such as distance from the sun, the level of heating received, the varieties of ices present, and the kinds of dust particles permitted in the surrounding haze. That said, at this point, it looks like the sun-facing aspect of the tail is hinting at properties of the ejected dust grains themselves, Perhaps that those grains are on the bigger side. We saw something similar with 2I/Borisov, where the dust particles turned out much larger than what's typical for comets in our solar system. The reasons behind that are still debated. But if larger grains are involved, they're less swayed by radiation pressure, making it far simpler to spot a tail pointing toward the sun with those bulkier particles. Does that click for you? It does. You can picture the whole thing by considering snow under sunlight. If it's basking in the rays, it melts quicker than snow tucked in the shadows. Exactly? Due to the direct exposure and heat. So initially, that material would seem to head sunward, but the sun acts like a fierce gale, driving it backward. You're dealing not just with light pressure, but also solar wind particles and various forces shoving it away, forming the signature elongated tail of a comet. One fascinating aspect of comets is their ability to generate meteor showers as you pass through the tail, which also opens up ways to snag samples from it. Those particles and dust particles in particular, I'm keen on grabbing some from 3I/Atlas. Could we launch a probe for sample return after the event, targeting the path it took to collect a handful of bits from 3I/Atlas? Is a mission like that feasible, even years later, say 2 centuries down the line? All right. Yes, your question has a few angles, and I'll try to cover them all. To start, I really appreciate your comparison of the sun warming snow on the ground. It's something anyone can picture easily. Did I cover your previous point on the tail well enough? The tail one. All right. Fine. Okay. A few ideas cross my mind there. First off, I'm a bit partial here, you know? Just on July 1st, I was deeply immersed in work on this atlas, and a team of us drafted that initial paper on its discovery in the opening days. I was pondering precisely what you're raising. How might we retrieve a sample from this thing? We knew we'd pile up observations, of course. It's thrilling, and it's fantastic how many folks hustled to gather data right after the find, which is all crucial and amazing. But in those early days, I kept wondering, how do we snag, as you put it, John, a few scraps from 3I/Atlas, or even just a handful? Yeah. Merely a couple of dust grains would do. Spot on. So, as you brought up, meteor showers are one avenue. Comets within our solar system do trigger them. Certain comets, particularly those nearing Earth, form these vast tails, and occasionally Earth plows through remnants as the tails fan out in various directions. Meteors often scatter in various paths before fading out so much that they're almost invisible. But occasionally, you get these spectacular meteor showers, and radar specialists who monitor those and log different meteor occurrences play a key role. There are detection stations scattered worldwide and even orbiting in space that follow meteor trails. From those readings, the pros can pinpoint what they term the radiant, the origin point where the meteoroid bits seem to slam into our planet from, and link it to a specific comet or dynamic asteroid. That way, you can actually identify chunks from comets or active asteroids that make it to the surface as meteorites, which you could collect if they hold up through reentry. That's what got me thinking. Okay, this is a bit mortifying to confess, but around July 5th or 6th, everything was a haze because I hadn't caught a wink of sleep while grinding on that research paper. Maybe I was losing it a little, but I started wondering, hey, could we snag any meteorites from C/2019 Y4 Atlas? Or might it drop some on Earth in the future? The short answer is a firm no, sadly. I checked with some meteor experts, and they basically said, Darryl, no chance in a million years, since it veers so distant. It's just too remote for any fragments from Atlas to reach us. In contrast, Oumuamua offered way better odds for meteoritic debris because it swung so near Earth. Despite lacking a prominent tail, we suspect it shed material due to its non-gravitational push, and its proximity would have made capture far simpler. The closeness to our planet is the biggest factor in whether you'll score any meteorite bits. So, yeah, nothing from Atlas, regrettably. Looking back, it makes total sense since plenty of comets zip around the solar system without yielding meteorites. We realize it takes a unique setup to generate a meteor shower, which isn't common among solar system comets, let alone interstellar ones that are far rarer. Thus, it's extremely improbable for material from a typical interstellar comet to end up as meteorites here. Now, shifting to your other angle, could we dispatch a probe for direct on-site analysis? Is that part of what you want me to cover? Yeah, but let's amp it up, Darryl. I'll raise you one. I'm posing a query no comet researcher has likely fielded on a YouTube stream. Picture a perfect scenario. A hefty interstellar comet barrels in, big enough for impact craters like we discussed, and we've got a sample return craft prepped to rendezvous. We snag our prize. But suppose we unwittingly grab a carbonaceous chondrite sample embedded in it, similar to that find in the Apollo lunar rocks. Is there even a slim possibility? Sorry, hang on, wait about that. My cat just plopped down on my keys. That's the mess you saw. It's captivating. My feline's intrigued too, though mine's quarantined in my separate studio, dozing in the sunlight, turning into a contented puddle. Anyway, back to it. Imagine our sample return effort targets a sizable interstellar body that's been pelted by meteorites from its home star system. Could we wind up with a treasure trove of relics from that original stellar neighborhood, still lodged there from ancient collisions? Might we distinguish layers, like, this resembles a chondrite but clings to an icy core? That's distinct, a separate fragment. In essence, could a single interstellar sample return yield double the payoff? Whoa, that's wild and totally intriguing. I've never pondered that scenario. But yeah, perhaps we could leverage it to push NASA toward launching a collider for an interstellar comet. It feels improbable, yet there's no real barrier against the main stopper I can come up with right now is why that idea absolutely couldn't pan out. All right, let's pull back a bit. If we're ever at the point, John, where you and I are chatting live about findings from an interstellar comet expedition, I'd say my career goals are fully met. I'd be thrilled just knowing we managed to reach one of those wanderers from beyond our solar system and maybe even snag a return sample. No hard feelings if the haul doesn't include micrometeorite bits or carbonaceous chondrite from the interstellar comet samples. To me, pulling off such a voyage would be an incredible feat in science and tech, a true milestone for humankind, targeting an object from another star system. If we're debating data meanings in that scenario, it's a dream come true. Though, I suppose the biggest challenge might be accessing that material. Keep in mind, these things zip by at insane speeds. Remember that paper we put together? The undergrad I've been guiding, Atsuhiro, just got it accepted. It sketches out spacecraft designs for rendezvous with Inyua. Wait, no, with 2I/Borisov? Actually, it was for 1I/Oumuamua, but anyway. We crunched the numbers a few months back when it seemed doable. The analysis showed that launching some repurposed Mars probes by late September could have led to a straightforward intercept with 1I/Oumuamua. That's off the table now, but at the time, we dashed it off in the early weeks, hoping a quick dispatch might work. The issue is the blistering pace of these objects. Factoring in the tight timeline, just weeks to launch, no years for fine-tuning paths, you need a ton of leeway for mistakes. That setup makes hitting the tail way more probable than nailing the core for any interstellar visitor, since the tail's this expansive, wispy cloud, as we've touched on, either pushed by radiation or venting from the comet itself. It's spread out over huge space, whereas the nucleus is a minuscule bullseye. So, yeah, in an ideal future, say, a decade from now, where we're spotting interstellar comets all over and firing off probes nonstop, that'd be awesome. But for the inaugural mission to 1, there's a solid chance we'd only graze the tail. And sampling just the tail? It skews your results, you know? You're sifting through vaporized stuff from the surface that hitched a ride, but mostly probing the sublimating ices, primordial remnants from how the comet formed or accreted. That's still viable science. Honestly, John, it's a brilliant concept, and yeah, it's plausible that an interstellar comet swinging through our system could carry meteoritic debris from collisions in its home system, stuck to its crust like some wild assortment. A real smorgasbord or smorgasbord, whatever, a natural sampler of its origins. That's my big picture pitch here, Darryl. Snag a broad snapshot of another stellar neighborhood, hand-delivered right to us. No need to trek out there. It's already crossed the cosmic void for you. But let's crank it up, Darryl. That's my style. Picture a crude trip way down the line to an outgassing interstellar comet. Would you sign on to be the first to plant boots, sort of, in another star's domain, even with all that CO2 and junk blasting off? You'd go, right? Yeah, I doubt I could turn it down. Sounds like prime material for a sci-fi novel, but wild that it might actually happen, not just fiction or something like that. That could actually occur during our lives. You know, it's not purely out of the realm of science fiction anymore, I suppose. especially now that we're seriously discussing missions to intercept an interstellar comet or something like that. Yeah, I reckon I'd struggle to pass up on it. Despite having zero interest in heading to space myself, if the chance arose to get right up to one of those objects and become among the initial humans to examine an interstellar comet so closely, who'd refuse? Absolutely. And you could explore other concepts too. Say, if it turned out to be an interstellar asteroid, just a rock hurtling by, and we're at the point of harvesting asteroids, someone might ponder, is there platinum in there? And head out to extract resources from that extraterrestrial material and process it. You get the idea? Yeah, you get it. Sorry, had you finished, or was there more on your mind? Nah, I just kind of wandered off into a chuckle, as I tend to do. Right. Anyway, another point is that, well, I'm stepping away from it, but I'm essentially serving as the early career logistics coordinator for NASA's Small Bodies Assessment Group, what we refer to as SBAG. Basically, NASA organizes these assessment groups, or AGs, which are meant to bring together experts. We host a few gatherings annually, pull in scientists from the field, and compile reports on our top priorities for NASA to tackle. Then NASA replies to those reports. You can check out SBAG online if it piques your curiosity. It's all out there in the open. We maintain public documents outlining our goals, like the key areas where we urge NASA to direct funding. There's a dedicated section in SBAG focused on human exploration, and since SBAG deals with small bodies, think comets and asteroids, there's real enthusiasm from NASA for crewed missions to these objects. That could mean putting a person down on an asteroid or a near-Earth object, for instance. Sure, asteroid resource extraction plays a role, but the primary driver is viewing it as a bridge to Mars. So, the idea you're floating isn't the wildest notion out there. We've got credible researchers, and NASA itself shows genuine commitment to dispatching astronauts to asteroids. Thus, while venturing to an interstellar asteroid or comet might seem a bit far-fetched, it's hardly an impossible pipe dream. Honestly, that proposal carried some real weight politically, since I recall Barack Obama floated the idea of heading to an asteroid. Nothing materialized, though. But yeah, it was on the table back then. I must have been pretty young when Obama brought it up. I hadn't hit high school yet, so I wasn't keeping tabs on politics much, I suppose. Totally missed that he mentioned it. I was, regrettably, in my 30s at the time, anyway. Moving on, next up, about 3I/Atlas and its composition. As the chemistry progresses, do you anticipate or recommend spotting intriguing chemical interactions or compounds emerging? I'm assuming that's the deal with this nickel. It's likely some nickel-based compound arising from other elements. Will you foresee it changing over time? And post-perihelion, after it swings past the sun at its nearest and peak outgassing phase, do you predict a shift in this object's traits? Yeah, solid question there. You're spot on. I meant to touch on the iron and nickel earlier. On the surface, that nickel spotting is odd because when they detected it, 3I/Atlas was still too distant from the sun for nickel to simply evaporate. So, I'm curious about the underlying reactions. What's brewing chemically? Precisely. The consensus is definitely that certain reactions are at play, producing the nickel. There are a few potential pathways, various chemical chains that could lead to it, and it's not fully nailed down yet what exactly. But broadly speaking, that's the current line of thought. Comet specialists lump it under non-thermal processes, indicating it's not due to sufficient heat for vaporization, but rather alternative mechanisms. Comas around comets host all sorts of fascinating chemistry, after all. So, we're undoubtedly witnessing that here, though the precise reaction pathway remains a bit mysterious. Absolutely. But it's incredibly fascinating since we're examining an object way older than our entire solar system. That's precisely what's on my mind. You know, how did conditions in the universe for star birth, accretion disks, debris disks, and planet formation stack up back then versus today? Any shifts? With a bunch more supernovae exploding nearby over time, does that alter things? Does the Milky Way's process for building rocky bodies change as it ages? Nope, that's spot on. Yeah, you're hitting the nail on the head, John. That's the big-ticket issue. From exoplanet research, we see that it absolutely does. Take one of the top empirical patterns in exoplanet studies. Hotter Jupiters are more common around stars with elevated metallicity, higher overall metal content. The straightforward takeaway? More metals in the protoplanetary disk too, since the star reflects that. Extra metals mean more planetesimals, comets, asteroids, and ultimately planets could assemble. Yet, as you point out, the Milky Way ages, more stars explode as supernovae, pumping metals into the interstellar medium. So, one theory is that older stars just end up more metal-loaded over time. That metallicity link, higher odds of spotting a hot Jupiter near a metal-rich star, might simply mean more such planets emerged in the later stages of the Milky Way's history. This interstellar comet, 3I/Atlas, is likely far more ancient than any solar system relic we've encountered, with some caveats we should mention, but it was screaming along at infinity speeds, which aligns with it being billions of years old, maybe even predating the solar system. It might hail from a planetary setup that arose in the early, low-metallicity Milky Way, before supernovae had flooded the galaxy with heavy elements. Perhaps its makeup stands out from our comets because it originated in a disk starved of metals, turning it into some quirky outlier. Just brainstorming here, but you get the idea? Totally. And which zone of its disk did it originate from? Well, given how loaded it is with carbon dioxide, it probably coalesced pretty distant from its parent star, huh? Right. Actually, early in the episode, I mentioned wanting to dive into the JWST findings. Yeah, JWST and SphereX detected the CO2, while Swift picked up the O and H2O. But anyway, that elevated CO2 to water ratio they measured is pretty striking. Picture it this way: H2O, CO2, and CO as the primary fuels for comet outbursts. Their presence hints at formation spots relative to the ice lines for each. In our system, for context, water ice starts around Jupiter's orbit, CO2 around Saturn's, and CO around Neptune's. So, heavy on CO2 but light on CO and water suggests it brewed in a prime narrow band. Out there, but not excessively so. Venture too far, and carbon favors CO over CO2. That's why those CO2 detections blow me away. They pinpoint 3I/Atlas to a tight slice of its protoplanetary disk. Even without linking it to a specific host star, it reveals tons of specifics about the surroundings where it took shape. Could that level of detail let us infer the star type it formed beside? Sure, it's almost certainly a red dwarf, but might the signature differ for, say, an F-type star system, and could we extract that info from an interstellar wanderer like this? Yep, that's bang on what my grad student is tackling at the moment. Bottom line, yes. You might not be able to precisely link an interstellar comet to a specific star, given the chaotic orbits across the galaxy. However, you can roughly gauge the entry speed into our solar system, which often hints at the originating star's type. Older stars in the galaxy tend to travel quicker overall. On top of that, the comet's chemical makeup points to a particular zone in the protoplanetary disk. Essentially, by piecing together these clues, the composition detected on the comet narrows it down to a specific disk area where CO2 can freeze solid, but not CO or water ice, and that varies based on the star's temperature. The incoming velocity adds another layer, suggesting the probable stellar categories it originated from. From there, you could refine it further. Once you've pinpointed potential stellar classes and snowline positions in the disk, factor in ejection by a giant planet. Drawing from exoplanet research, we can identify which stars are prone to having massive worlds in the ideal spots to fling out a CO2-laden object like 3I/Atlas. That approach could really help pinpoint the prime candidate host stars. Keep an eye out for updates on this. My PhD student, Tessa Franke, you've had her on the show before, is diving into that work as we speak. Expect some findings in the coming months. Sounds exciting, can't wait. All right, Gerald, great having you back, and I'm eager for our next chat as we build out more details on 3I/Atlas and upcoming interstellar visitors now that the Vera Rubin Observatory is operational. For sure. Appreciate it, John. Thanks, Ross. Always enjoy it. Event Horizon and my channel are now podcast ready on Apple Podcasts, Spotify, and YouTube memberships, with early access to ad-free shows, extras, and chill-out episodes. Jump in today via the links below for your go-to app. Heat. Heat. Music. Applause. Music. Heat. Heat. Music. Heat. Heat. Music.